Hi, my name is Charlie Hertzel, and today I'll be talking about Resonate, which is a runtime risk assessment framework for autonomous systems. So first, just a quick introduction to safety risk management approach to safety. So as this quote from the FAA handbook mentions, risk management has become kind of a core component of safety assurance in the autonomous aerial system domain, as well as in several other domains. And this approach generally starts with identification of hazards and the risk associated with these hazards, as well as procedures to control those hazards or mitigate the risk they pose. The risk is typically defined as a product of severity and probability of certain consequences, often using a risk matrix like you see here on the right. So this generally starts where you identify your risks, you assign a severity to them based on how their kind of potential consequences, you estimate the probability of those risks, and then you implement control strategies to try and bring that risk down, either reduce the severity or in this case, reduce the probability. And you try to bring that risk down from the red here, which is the unacceptable region, down into a more acceptable region. So the conventional techniques for this use static design time estimates, which cover the range of expected operating environments for the system. However, that's not necessarily sufficient for highly autonomous systems where you're constantly dealing with potentially hazardous events in highly dynamic environments. So to address that, we introduced Resonate, which is a framework that calculates the probability of consequences dynamically. So the probabilities of a certain risk or a certain consequence may change based on the state of the system and the environment. That may change the likelihood of certain events, become more or less likely to occur, and then the effectiveness of our control strategies may improve or decrease based on certain changes to the system or environment. And so that can have the effect of making a particular risk or a particular consequence more or less likely. For now, we treat the severity of any consequences static. So with Resonate, we use an extended bow tie diagram to describe how hazards can propagate through the system and escalate from relatively minor events and become more serious consequences. We then make design time measurements of the conditional relationships between particular hazard rates and the state of the system and the environment. Using those design time measurements at runtime, along with observations about the system state, we can then dynamically estimate the risk posed to the system. And finally, we implemented Resonate on an autonomous vehicle example in Carla, which we'll talk about here in a moment. So this is a kind of a flow chart for Resonate, broken into design time steps on the left and runtime steps on the right. So the first steps, system analysis and hazard analysis, these are pretty much the same as more traditional techniques. Even the bow tie modeling is not itself new. This is used to describe how hazards can propagate and escalate. However, what is new is where we measure conditional probabilities for this bow tie diagram. So for instance, these barriers, the blue blocks in these bow tie models can change, their effectiveness may change based on the state of the system. So we observe in simulation what those relationships are, and we encode that information into the bow tie diagram. Also, assurance cases are commonly used to explain how the system achieves safety and what measures have been taken. Then at runtime, the Resonate risk computations take in the bow tie diagrams along with those estimated conditional probabilities, take in other information about the system, such as sensor observations about the environment or the system, any hypotheses about particular failure modes that may be present from a suitable fault diagnosis engine, and then any other runtime monitors which may give us an indicator of how the system is doing. This can then produce a dynamic risk estimate, which we can feed back into our assurance case to evaluate if our evidence is still valid in our assurance case, if our goals are still satisfied, and then into a decision manager to make decisions about any necessary mitigation or contingency actions. So our target platform is an autonomous vehicle in the Carla simulator. You can see here as it drives through a city with 3 forward-looking cameras. The images from these cameras are fed into a neural net, labeled here the navigation LEC, or learning-enabled component, which I'll address in just a moment. This neural net produces waypoints These are very fine-grained, detailed waypoints at a sub-meter level, which tell us how to control the car. In normal operation, this passes through a supervisor and goes to two PID controllers, which produce the commands for steering, throttle, and braking of our car. Now, we also have an emergency braking system, which is radar-based and independent from the camera images. So if this system detects that we're approaching an obstacle too quickly, then it will signal a brake alarm, and the supervisor will override our normal LEC control and apply a brake command to the vehicle. So as I mentioned, our primary control is done with an LEC, or a learning-enabled component. In this case, it's a type of machine learning neural net. But in general, an LEC is any component where behavior is learned from data instead of explicitly defined. And these types of components are prone to the out-of-distribution problem. This is a situation where the LECs, they predict poorly on data that was not trained on. So if the data is outside of the training data realm, then the LEC will perform poorly. Now, normally this is hard to detect. It's hard to know when the data you're giving the LEC is out of distribution. So we use an assurance monitor, which is trained along with our navigation LEC here. We use this as a out-of-distribution data detector. So this component gives us some indication as a confidence level based on how well our LEC is doing. For this system, we are interested in the roadway obstruction hazard. So we don't want to collide with any kind of roadway obstruction. You see here. For this hazard, we identified a couple of different threat conditions or threat events. These threats are shown on the left, so that's either pedestrians could walk out in the road in front of us, or a vehicle may come into our lane, either by changing lanes abruptly or running a red light, running a stoplight, so on. The blue blocks show our barriers or control strategies for limiting the propagation through the graph. So our first line of defense is we simply train the LEC on a diverse data set, which includes both pedestrians and vehicles entering our path of travel. If these barriers fail, so say a threat occurs, a pedestrian steps out in the road, if our LEC fails to recognize that, then the threat may escalate to a more severe event, which is a top event in this case. So this is where we're approaching the obstruction unsafely. Then our second line of defense would be our emergency braking system. So if our emergency braking systems detect that we are approaching an obstacle unsafely, it will override and stop the car. If this barrier also fails, then the consequence may occur. So effectively, each barrier here just reduces the probability of the hazard propagating further into the graph. Now, as I mentioned before, these barriers have conditional relationships with the state of the system and the environment. And so this page here, this figure shows that same bow tie diagram, but now with some of the underlying equations shown on the figure. So these different functions and their meanings are outlined here at the bottom of this slide. But in general, we see these numbers are given in times per minute. So we see pedestrians we found stepped out in front of the vehicle about once per minute. A vehicle entered our path of travel about 4 times per minute. So this is a relatively rude driving environment. FS gives a severity of events. So we see these threats are benign by themselves, so they have a none severity level. And then as we escalate through the graph, we see minor severity level for the top event and then catastrophic severity level for the consequence or the collision. FB, there's 2 of these functions, and these give the probabilities of, or the effectiveness of the barriers B1 and B2 for this function, B3 for this function at the top right. This gives the effectiveness of those barriers given a particular state. So in this case, this function has a lot going on, but it's essentially a continuous part based on the output of the LEC assurance monitor multiplied with a discrete part based on whether or not certain fault modes are present, as shown in this table here. And then the function for barrier B3 is a little simpler. It's just a piecewise function based on the level of precipitation detected in the simulator. So this bottom function here, this is the relationship between how effective our barriers B1 and B2 are given the output of the LEC assurance monitor. And this is just a sigmoid function, which you see here plotted. And so essentially how we come up with this sigmoid function is we set up simulated scenarios where we know threat T1 has occurred. Now, knowing that T1 has occurred, we randomly sample a lot of different simulated scenarios, and we observe how many times the top event has occurred. Now, given that we know T1 occurred, we can look at how many times the top event occurred and determine the effectiveness of barrier B1 under different conditions. Using, in this case, maximum likelihood estimation, we fit that data, and you get the plot you see here on the left. Now, the y-axis here shows the probability of the barrier failing, so higher numbers are bad. Similarly, the assurance monitor is provides kind of an inverse confidence. So a low assurance monitor output indicates the LEC is performing well. So you can see when the LEC, the confidence in the assurance monitor is low, indicating good, then our barrier failure probability is significantly lower. And as the assurance monitor output goes higher, that barrier failure probability also goes higher. Currently, like I described, we set up these isolated scenarios in simulation. But in the future, we want to look at trying to continually improve those estimates from operational data as more data comes in from the system. So this shows an example of the vehicle operating in the simulator. And in this case, we'll inject a camera fault where the camera is occluded. Our occlusion detectors notice that, and we see our risk score goes up. In this case, our assurance monitor is only somewhat of a weak detector of that fault condition, so it goes up a bit, but it doesn't go very high. And then here in a moment, we'll see the camera occlusion clears, and the risk score will quickly return back to nominal. So there, the occlusion is cleared, and now we see the risk score coming back down. The assurance monitor has gone down, and it normalizes down at the nominal value. So that gives you kind of an intuitive understanding of what the risk score means. We also wanted to validate it against the observed number of collisions. So we ran 608 simulations over a variety of scenes and weather patterns. And we model the occurrence of a collision as a probabilistic event using a Poisson distribution. So Resonate is essentially predicting the lambda parameter of that distribution, or the hazard rate, and we can compute the probability of a collision in the next time period with this equation here. So again, these plots here show kind of the same intuitive feel that as faults occur, the risk level goes up. But we're more interested in validating that these numbers match, that the estimated rate of collision matches the observed rate of collisions. So this shows 6 different scenes, S1 through S6, where S1 is kind of a nominal, everything's good scene, and S6 is a highly adverse scene. And we see the blue bars show our estimated collision rate, and the orange bars show the observed collision rates. So you can see a pretty good agreement all the way up between the two. Some more validation with the same data, we found that our dynamic estimate far outperforms the best static estimate with a log likelihood of -710 versus -741. And this, I mentioned this is a best static estimate because this is a posterior estimate, which is derived from the observed number of collisions, the average rate of collisions, and our dynamic estimate does not have that luxury of knowing the outcome ahead of time. So we're still able to outperform it with that. We also see a good correlation rank here, score. And in this plot here, you see the green line shows the fit to all the data. It's a good positive correlation. It's not quite 1-to-1. The red line shows the fit when you restrict the data to just the 0-to-1 range. So we see a much closer to 1-to-1 ratio. So we're looking into why we tend to overpredict the risk a bit when we're predicting above 1. Next, some overhead of Resonate. It's relatively minor. It's significant at first when you first look at the numbers, but however, that's mostly due to the usage of the assurance monitor, which is also deep learning based. The actual risk calculations only take about 0.3 milliseconds. So if you are already using certain runtime monitors, which you likely would be doing for any kind of safety critical system, then adding Resonate risk calculations on top of that does not add much overhead. We have a second example here, which is a UUV following a pipeline on the seafloor, while also performing obstacle avoidance. I don't think we have time to go into that here, but we do have a demo available on our GitHub at this link for those that are interested. So just to quickly conclude, Resonate provides a technique for dynamically estimating risk posed by identified hazard conditions. It does this by allowing the probability of threats and the effectiveness of barriers to change based on the state of the system and the environment. We saw that the estimated risk levels agreed pretty closely with that observed in simulation, and that the overhead from the adding resonate risk calculations is relatively minor. However, I should note that the additional overhead from the additional runtime monitors can be significant. There's a couple of avenues for potential future work here, which I won't go through each one, but feel free to read through those. And thank you for listening. Bye.